Everyone, welcome. Hello, everyone. Welcome back. I hope you've got a chance to go through the material we have shared earlier with some updated information in the emails yesterday. We will have a session in the beginning now for about 15 to 20 minutes, or taking your questions as well, and discussing the results and the analysis for the task we gave yesterday on the structural assessment part. And then we will move on to the system resilience or system reliability assessment with the codes June explained yesterday. Let me share my screen and we can get started. Am I sharing the right screen?
Yes.
Okay. Okay. So we had the first task was to identify this typology. Before we begin, anybody has any comments or anything they want to share before even we begin? I hope you were able to access the material in the first instance. Anybody stuck with not even able to access them? You could put any comments in the chat or raise your hand, or somehow let us know if there is any trouble. So if we get on, we had this details of this RC school building. The task was to identify the parameter attributes for the glossy taxonomy parameters. So we can. Oh, we were also given the additional information on the plan and elevation, some of the section details for the columns and beams, and some additional information about the design features of this building. So we can look at this in detail now. We can see there are RC frames with infill masonry walls with no evidence of any isolation of the infill from the frames. Plus, we see some of the short column short column features in these frames. So we can classify this frame, the main structural system, as the RC3, short column moment resistant frames. Next, we look at the number of stories. It's a two-story mid-rise building. With the features given for the seismic design features, the age of construction, we can assess that this has a low seismic design level. This doesn't seem to have any irregularities. It's a rectangular plan building, and no irregularities structurally in the vertical direction. We can see that the span is less than 6 meters between the frames, and hence it can be called a short span structure. This information was already given that the building has a rigid foundation, as it is not visible from visual surveys. We see that this building has no pounding risk. It's an original structure with no evidence of retrofitting or strengthening for seismic capacity. Overall, it seems to have good condition. It can be subjective. Some of you might feel this fair condition, or some of you might feel it's good condition, but in any case, it's not directly highly consequential to the final results. Now, with the inside view, we can look at the dimensions of the columns and beams, and also from the given information on the sections. We can see this has comparable dimensions both for the depth of the column and the beam. Hence, it can be called a regular or strong column structure as compared to a weak column structure where the columns are smaller than the beams. The diaphragms are rigid RC slabs, and we don't see any non-structural vulnerable elements such as the false ceilings or the large bookcases that can be causing a threat to life. So combining this, we can then create our taxonomy string for the structure. You can fill in these parameter attributes and then create the taxonomy string. So this is the first assignment we had. If anybody has any troubles or any questions regarding this, we can take them now. Do we have any? No. Okay. So if we move on to the second task, we were given the details of retrofitting provided to an RC school building, where the masonry infill walls are now isolated and the steel braces are introduced. So we were asked to do the seismic performance assessment using the N2 method, first to identify the performance points, the IMEDP points, and then to conduct the fragility derivation and vulnerability derivation. So we can, this is the detail given, the capacity curve with the base shear versus roof displacement. We can already see that this is much better capacity, both in terms of shear capacity and displacement capacity as compared to original structure. When we conduct the N2 method, we obtain the new performance points for the retrofitted structure, which can then be inserted into the fragility derivation app, the MATLAB-based code that was provided to obtain the fragility functions, and then followed by which you can use the fragility to vulnerability converter tool to produce the vulnerability function. So we see that for the normal range of ground motion intensities, the vulnerability is significantly reduced. Say, for example, even up to 1G, we don't have any significant vulnerability. It's still less than under 10% MDR. So this is the end of our results. If you want to go through the material and have a live analysis of the content, we can do that. But we are more interested in knowing how you have approached it. How have you found it? Are you able to get the intended results? So please feel free to have your voice heard. If you would like to unmute and ask questions directly, you're welcome to do so. Please let us know so we can enable that. Or you can put your questions in the chat or Q&A session. If you, I wanted to mention some of the things. Unlike the first case of the original structure that we discussed in the class or in the session yesterday, we had slight differences that we introduced in this. So here is your input function. Sorry. Here is your input pushover curve for the RC retrofitted structure. So you need to make sure that you have the information correct. You are given the threshold values, which is now different from the original structure. So we update our N2 N2 Excel file with the new information, the new input. Here is the new capacity curve definition. So you need to make sure that we are retaining only the necessary information. If any previously run information data is available, is existent in this column, make sure that you delete them. And also please go and check every time that this green columns are updated. So this is calculation of the equivalent STF capacity curve, the single degree of freedom capacity curve. So you need to make sure that this is calculated for the entire range of values. There's another thing that you might find different from the previous one, that calculation of this idealized capacity curve. This uses the principle of equal area under the actual curve and the idealized curve. So here you can see the area under the STOF curve and area idealized curve. This is calculated area under the STOF curve. This is calculated as a sum of sum in the column that is hidden here. So if your idealized capacity curve doesn't appear correct, please make sure that this column, even though it's hidden, it's also calculating the values for the entire range of the values in the green columns. So this here has a value of calculating between the rows here. So once you have these ready, you should have your idealized capacity curve corrected, and then you can, as we did yesterday, we can run the okay, for now the macro is disabled. We can enable the macro to run the analysis. This is okay, this is not. So here is your N2 method. We are dealing with the retrofitted case now. Here the macros are already enabled. We can run the EDP file, EDP function. And to obtain your performance points. So we have the performance points ready. You can go to the LSM input file, which is which comes along with the MATLAB code, MATLAB app. So you would insert your performance points, the IMEDP points here, update your threshold values, the slight, moderate, extensive, and collapse damage limit states, and you can run the close the function, run your MATLAB code. So we have the tools, LSM fragility, and you can run the fragility vulnerability app. Hope this was fine for all of you, and you're able to generate the fragility functions, and then go back to the LSM function, LSM input file to extract the input, extract the fragility function parameters. So once you have the parameters, you can go to the fragility to vulnerability converter, insert your fragility function parameters here, and then generate the new fragility and vulnerability functions. Sorry, new vulnerability functions. This is the fragility function, which is the input. So I think this completes our problem. This is still running. You can keep asking, putting your questions in the Q&A, but I have to leave slightly early today. So if you could post your questions in this section before 3:30, that would be great. For the time being, if we don't have any additional questions, we can move on to the next section with Dr. June.
Thanks. I have a question. So how is this retrofitting being considered in the model?
It's basically the capacity curve that is derived for the new model is updated. So it's okay. Let me share again. So we have the input itself here. If you see, this was the capacity curve original structure when we run a model analysis using a pushover method for the original structure, and this was for the retrofitted structure. So it's basically included in the model development itself in the numerical platform. The second or the next updation is with respect to the damage thresholds for the derivation of fragility functions. So we know that
and this derivation is based on the capacity curves.
Yeah. So once the capacity curve is updated, you are going to get different updated results. Yeah.
Is it usually straightforward when given the retrofitting plans to calculate a new capacity curve?
It's you really have to rerun your analysis. Like as we discussed yesterday, we can have a model generated, a 3D or a 2D structure generated on a platform, say for example, a finite element analysis software or any other like applied element method, you can generate a model, run your pushover analysis, and then you update your model with the structural elements of your retrofitting, and then you would take out your new capacity curve. So that particular part we are actually omitting from all of our discussions,
Mm.
and we're starting this analysis from the capacity curve onwards. So
Right.
modeling the structure and forming a pushover analysis or any kind of dynamic analysis is a different topic for discussion. So we have previously done a course on using OpenSeas for modeling and analyzing structures. There are also several methods, modes where one can do the modeling and analysis.
Mm.
Yeah.
So how should we proceed now?
Yeah,
Do
yeah.
do you think giving a few minutes
Yeah,
for
we can.
everyone to take uh give it a go to your
Yeah,
exercise and come back?
yeah, yeah.
Mhm.
If I don't see any questions in the chat box, but if you have if you could give it a go and see if your programs are working on your system, if your installation is okay, please let us know.
Mhm.
You can also let us know afterwards if you haven't managed to do this before the session today. So please, you can contact us via email or let us know if you have any trouble. We received some requests yesterday to provide the links to the previous recordings. We will put that in the chat now. It's you can always go to the UNESCO Chair website and see all our previous recordings there.
Yeah. Then we start at 1:30 for the second set of exercise, and we will give people
Yeah.
around 10 minutes.
Yeah.
Yeah.
Just a second. I think there is a question about how can we do performance-based design in retrofitting work. So basically what we have done right now is a performance-based analysis. So we haven't designed the retrofitted like the retrofitting for the structure based on our analysis, based on a design, but we are taking a structure which is now retrofitted and analyzed it to obtain this new capacity curve. So you can look for the performance-based design approaches where you would set targets of your displacement and shear capacity and then design for it, which is currently out of scope for this presentation, but we can come to that maybe another topic for discussion. Um, okay.
Okay.
Yeah, I can stop sharing and
Hey, there is
you can.
another question from Abbas.
Okay.
How you can
Okay. Show the damage threshold and final fragility parameters. So of course. So let me share again. So we have used the fragility parameter, sorry, the thresholds are here for the retrofitted structure. So if you see the pushover curve, um, it's your first slight damage threshold is defined around 0.03, which is towards the very end of your elastic range. The second damage limit state, the moderate damage, is at 0.06, which is around where the inelastic deformations are just beginning to happen. And the life safety and collapse or the extensive damage and the collapse are at 0.11 and 0.2. So 0.2 is basically where we think we are defining the collapse, and 0.11 is where we see the life safety or the extensive damage limit. So these are the thresholds, damage thresholds. If we go to the fragility, you need to open the LSM in file to get the fragility parameters. So since we have just run this analysis, you will be able to see the results here. So the fragility mean and standard deviation values would be written into this file, as I explained yesterday. So here you get your results, and here you can see the plot of this new set of fragility functions. So you can see that in comparison with the original structure, this has shifted to the right. So say for any for 0.5 PGA or IM here in this case was spectral acceleration, you have really moderate damage is nearly certain. It's 90% chance of moderate damage, but in the retrofitted structure at 0.5, the same IM level, you don't have any chance of moderate damage, and you only have a very slight chance of um, slight damage. So this is how we see that the retrofitting has improved the seismic performance of the structure in shifting the damage, the fragility functions to the right. So I think could you explain how did you select the ground motions and use the worksheet? So these ground motions are basically selected from I think the far field ground motions from the FEMA guidelines. You can use any set of ground motions. You can select the ground motions based on, certain parameters that are relevant for your region. So for example, you can consider the distance to the fault, the magnitude range of the fault near to you. And you can actually choose what number of parameters you want to consider as a criteria for sorting or selecting ground motions, and you can use your own set of ground motions. You don't have to use the set of ground motions we have used in the Excel file, but this is a generic set of ground motions which are used for generic purposes because we can use them for generic cases. So this is about ground motion selection. Again, is another very big topic, and I think we can use any of the ground motion repositories and provide the sorting parameters or the what do you call the criteria for selection, and then select your set of ground motions. And we have used the scaling, I think 20 scaling parameters. So each ground motion is then scaled 20 times so that we get enough data points for regression. So thank you. My threshold was a bit different. Okay. I have updated this threshold in the email that I sent yesterday. So you might have received an email, I think last Friday. So please use the files that are sent in the latest email, okay? That was sent last night, yesterday. So if you have any trouble with those, please let us know again and we can send you again.
Are there like standard rules when you decide this thresholds?
Yeah, it's generally you can look at the curve and decide. Say, for example, you know that in the elastic range, you don't expect to see damage. Yeah. So once you cross the elastic range, you start seeing slight damages. And then as you progress, the damage also increases. So if you're doing a numerical analysis on a model, you can actually correlate uh, the level of damage with the on the curve. But there are also several guidelines like we discussed yesterday which give you indications of what can be defined as a slight damage or what can be defined as a moderate damage. So this is defined. Say, for example, RC buildings, you can have primary structural elements, secondary structural elements, and for each of the structural elements, what level of damage can be called moderate or extensive is defined. So that's the indication. And it also gives us some values of what level of roof displacement um, can be an indication of each damage level. So if your structure is pretty standard, you can go for these values prescribed by the guidelines, but otherwise it's always good to have a model built for your structure and then do an analysis. So that will give us what can be the range for each damage state.
So we need to connect with illustrative explanations of each damage state to some numerical observations
values.
from
Yeah,
these
exactly.
structural outcomes, let's say.
Yeah. So
And so
I think
usually the slight damage is when the elastic response ends, and
I think we had a short brief discussion on this yesterday. Like if you see here, you can have a global slight damage. This is in the case of RC structure or a masonry structure. You see that the walls only start getting very, very minor cracks. At the next level, it starts, the cracks get more and more from here. And the third level, it's already starting to affect the structural stability. But the structure at this stage is still, it's stable enough that it doesn't kill people, both in terms of structural elements and non-structural or secondary elements. And the last limit state, it's where, it's still supposed to take the gravity loads, but at least in the case of RC frames, but already you have started forming the hinges and the stability is lost. So it can be different for different structures, and also depending on which standard you're using as a definition of performance level or damage level. So here, for example, for concrete frames, as per FEMA, these are the limits given. So here you can see what is constitutes as a life safety limit in primary or structural secondary elements. But if you see, for example, EC8, this could be slightly different, but in general, they indicate similar levels. So that's the idea.
So the slight damage is still within the good range of elastic behavior. So in the middle.
Which one?
The slight damage. So
Slight damage. This is actually, the slight damage is not even included here. Because it's still even before this. So this starts happening, say, for example, moderate to extensive to collapse. So you can either define in terms of damage states or in terms of performance levels. So the terminologies like immediate occupancy, life safety is indicating the performance rather than the damage. So when we have, say, yesterday somebody was asking about this as well, that we have a system level analysis, for example, we have different types of structures we are combining together in a system. So it may be sometimes beneficial to discuss in terms of function or performance rather than individual damage. So it can be mapped from one to the other, basically, depending on what is our need. So I think there are some more questions. So no, I think these are now answered. Okay, I think if we have no further questions, we can move on. Jiyun, thank you for the questions, and I hope it's all clear now. Yeah.
Okay, then I think we can move on to the second set of exercise, and we can make this kind of a free form that we will stay here until the planned seminar time, and you can leave if you don't have any questions and you successfully ran all the analysis, and we will take that as a sign that that you had no problem with the exercise problems, and we will close on the scheduled time. Does that sound reasonable? Okay, great. So then this second set can be found in the link that I just put on the chat, but this can and this is the same link that we shared yesterday by in the Asana's email. And if you visit this out, I haven't shared my screen, have I?
Yeah, we can see the screen.
Yeah. So this is a tutorial that you can find this tutorial at this link, and if you go to this Google Colab, so for the papers, you can refer to these papers to get the theoretical background, and you can find and you can use this Python script on this Google Colab. So if you go to this Google Colab, then I also left the instruction on how to use Google Colab. So you can, or just pop it up here, that you can use this open the, no, I was already in the notebook, right? So you have this when you have this open notebook chat, then you can enter, you go to GitHub and you can enter this URL, and if you click the search, then you can find these. And today we're going to look at this second set. So, and this is how it looks like. So first, if you run this cell, then this is basically to clone the data sets in the GitHub, and we also need to insert this MBNpy package. Other than the MBNpy package, everything else are just the classical Python packages that we use. So now it is inserting. And if it asks to restart the session, then you can do it. It shouldn't be a problem. It just sometimes requires us to restart the session when we install a new package. And now we can run this code, this cell, which load all the necessary packages, and you can download this this Excel file, which includes the information about the screws damage. So if you go to data, then you can check this file. Oh, I can't visualize here, but we can see here where there are 10 buildings for screw A, and there are around another 10 buildings for the 11 buildings for screw A, and the 9 buildings for screw B. And there are these classrooms with different number of classrooms, and there is this fragility curves, fragility parameters of mean and standard deviation that we just saw during Asana's presentation. So we have 2 scores, and these are just to get these building names and just for repository purpose. And we are setting this PGA as 4G, 0.4G, which is the 2,500 year return period intensity measure for Cagayan de Oro in the Philippines, where these data are from. So, and if we go to the bottom, then the final objectives are twofold. First, we want to calculate the system failure probability when given all these fragility information about the screw buildings. So here we will get something that's very low number, which is 0.007%. And we will also get the relative importance of these school buildings for school A. And we will be going through only school A, and I left school B for your own pleasure. So then with all these preliminary data, we can now start building an MBN. So if you recall yesterday's presentation, you can find it over here in GitHub repository. Then we had this structure where now these component events are the buildings, and this S is a school complex, which represents the system event. So now we need to define the distributions over these component events and also the system event. And for the system event, we are going to use this BRC algorithm, which defines this optimal decomposition to build the system's event matrix. So first, in MBNpy, you need to define these two things, the variables and the CPMs. So that the variables store the information about variables, and CPMs, conditional probability matrices, store the information about probability distributions. And there are two other inputs that are necessary for BRC algorithm, which are the probabilities of the components and also the system function. And the reason that we are using this dictionary for probabilities to define the component probabilities which are already present in this probability distributions is because we wanted to make BRC implementable even without this full construction of MBN. So that's why we are repeating this information, which is actually present in here. So to construct these three data, so we are going through each school and we are going through each building. And for each building, we are getting this number of classes just for information's sake. And first, we need to define this variable which we are defining in this dictionary. And this is the object that we can bring from the MBNpy package. And we need to provide two information. The first is a name. So name is just a building name, and which we have information over here. And it will be A01, A02, etc. that we just stored in this build names. And second, we also need to define these values. So this means that here, this means that we have two states for this variable. And the first state denotes that the available classroom is 0 because the building has been extensively damaged, so no classroom will be available. Or if it is not, then it survived, and it can provide this number of classrooms. And we can also get this failure probability using the fragility course. So this PF is what we previously calculate over here by using this mean and standard deviation of the fragility course. So we obtained already these probabilities for each building code. So we are retrieving this value. Then we are storing in both probabilities and the CPMs. So in the probabilities, we are informing that the state 0 happens with this failure probability, and state 1 is happening with the probability of 1 minus the failure probability. Then for CPMs, we need to use this CPM variable, which is also from MBNpy package. And for this school, they don't have any parent node, so they have only themselves in their scope. So we include them just that the variables are just themselves, and the number of child is 1 themselves. And the event matrix includes either it fails and survives with the probability of failure probability and 1 minus failure probability, which is the survival probability. Then if we go through all this building code, then now we can store also this core node, in which case the name is core. And we say that the state 0 it represents a score failure, and state 1 represents a score survival. And the reason that the state starts from 0 is because Python is uses zero-based index. Then we also need to define this PM, conditional probability matrix, using this object, where now we have variables as a score. So in this scope, we have score and also all these component events. So we need to, we have this, all the variables that are, that has the building, which are the buildings of this school, and the number of children again 1 because S is the only child and all else are parent nodes. Does that make sense? Okay, then now we are moving on to the system function. So this is the last input that we need to define. And here we are the first input should always be the component, always should be the component state. So that this component state will put what the state of these component events here, the building variables take. And this score name is just to specify, so this should be actually score A. And this threshold means is used for the is used for the to define the system's survival or failure. So here we are defining the system survival as if the available number of classrooms is greater than or equal to the threshold multiplied by the total number of classes. So here by defining that the threshold is 70% means if we assume that the school can run if at least 70% of the classrooms are in operation. Then we can get these total rooms by looking at the school's values, these variable values that we stored in the for state 1. Then we now count the number of available rooms. So going over each component and state, we check the correct number of classrooms. So if the state is 0, then it will return 0. And if the state is 1, then it will return the available number of classrooms. Then we can add this number. And by going through, we can check how many school buildings are available given this component state. Then if this number of available rooms is greater than the required number, then we conclude that it is system survival. Then this is really optional, but I just wanted to show how you can return this minimal component state to make the BRC algorithm more efficient. So if you can, then you can provide by looking at this component state, what is the minimal buildings that are required to satisfy the system state. So what this basically does is it goes through all the component state that survived within this particular given state. Then if it is survived, then it adds it in the minimum component state. Then it stops if the current room count is already greater than the necessary number, which means that even if there are other survived buildings, they are not necessary to meet this minimum requirement. And of course, if the number of available rooms is less than the threshold value, then we return system failure. So the system state should always be given. This is rather optional. This is also for information's sake. And mean component state, they could be set as either none, or if it is possible, you can give some more information. So let's see how this system function works. I'm not sure if I run this as well. So here, then if you give the component state that all the component has survived in this square A, then if you check this available room system state and the main component state using this component count classrooms and this component state, then in this example one, you get there are 102 rooms available and the system state is S, survival. And the minimal component state, it says only this the survival of these 4 buildings guarantees the survival of the failure because they have these capacities which are much higher than other buildings. So, while there are 102 rooms available, we can guarantee that 70% of this number can be achieved by the survival of only these 4 buildings. Then in example 2, we make this first building to fail. Then now we have only 78 rooms available, but still the system survives. And we now, but for this one, now because we have A1 failed, we need much more buildings to guarantee that the system survives. And finally, in this example 3, if we make this A2 fail together, then now we have only 56 rooms available. So now this function returns system state as failure. And because we are not returning any information here, so the minimal component state to guarantee this failure is returned as none. Then the BRC algorithm will internally try to figure out what caused this failure in this case. So then now we are ready to do the system reliability analysis, because if you recall, here we didn't specify the event matrix and the probability vector for this system event, and that was because we didn't know. So now we are going to quantify this event matrix using the BRC algorithm. So this is, we are repeating over here. So BRC algorithm will run this decomposition, and then it will return this C matrix. And because this is a deterministic function, we will get a probability vector of 1. So we say that we are going to look at this square A. Sorry, this is a old version. And then for system function, now we need to use this lambda function because BRC algorithm requires only one input. So this is because it will try different component vector state to infer the rules and the branches. So by using this lambda function, we can specify that these will be just fixed for the and only this one will be changed, and this is implied here. So now we can run this BRC function by providing these probabilities and the system function. And we can get these branches and the rules, and these are just for information's sake. So if we run this code, then it's quite fast because this is a very small example. So now we can see that it completed with 121 branches, and it ran 78 times of the system functions, and it got 35 conditions for survivor and 43 conditions for failure, and the failure probability is this much. So if we look at, for instance, something like if we print the rules, the survivor rules, you can say for I image. So if we look at the first 5 survivor rules, then we have these ones where if these 4 buildings survive, then the systems survive. If these buildings survive together, then the system's survival is guaranteed. And if we do the same thing for the failure rules, then we can say that the failures of these two buildings lead to system failure, and all these combinations. So now we need to convert this BR branches into the C matrix so that we can use for this C matrix, event matrix. And here we have, we need to provide the two inputs. So first the branches, and second one is what is the order that we are going to use for this event matrix back from the columns. So we need to say that here we are saying that the order of the column will be A01, A02, etc. until A0, A10 or 11, I guess. Then we are removing some miscellaneous unknown branches. So if you get this one, then you will get 0 for system failure, 1 for system survivor, and there could be some unknown branches, which is returned as 2. But the reason that there are remaining unknown branches is because there are some 24 unknown branches, but they have too low probabilities for Python to differentiate with 0. So that's why this algorithm has stopped. So we need to ignore this one. And this is why I'm removing those ones that has this first column state, which is the system state, as unknown. And in this way, we can construct the event matrix. And again, the probability matrix will be a function of an array of 1. So we just create this MP1s and we put this, complete the distribution of this score. Then now we are ready to do inference. So this is what was explained over here, where we looked at how variable elimination eliminate each variable from the Bayesian network, so that in the end we leave only the one that we are interested in. So here we can specify the variable elimination order that we want to eliminate each of these buildings. And using this inference module from MBNpy, we can use this function variable elimination, and we provide the CPMs that we just constructed, and we provide this variable elimination order. Then this MSys is returned, where all the variables but the systems one is remaining. So here we can get this marginal distribution, where the first state, which stands for system survival, has very high this 9.993 probability, and for this one it has around this probability for system failure. So we can say that the system failure is quite low. And another thing that we can check to further support decisions is this relative importance of these components, which are defined in many different ways. But I just brought one of those where it is defined as a conditional probability that if the probability that of this building has failed if the score has failed. And by Bayesian theorem, this is derived by the intersection probability divided by the score's failure probability. And by definition, this probability measures the relevance between this particular building's failure and the system's failure. So and we call it conditional probability importance measure, so CPIM. So and to get this, we need to get this intersection probability because we already know this score's failure probability, which is this value. So we already know this, so we can get this probability by using this marginal distribution by getting this state 0. And now to get this one, we go over each building. And this time we use this variable elimination, but we eliminate all buildings except for these that has the building that we are interested in. And in this way, we can get this joint distribution where we will get similar probabilities distributions, but this time we will have one building added at a time. then we can get the probability from this one, where we are interested in the probability that both fail together. And we can store this value where this is a joint probability, and this is the system's failure probability. And if we store all this, we get these values. And if we plot the if we run this one, it is rather quick. And if we plot the CIM, then we see that A01 and A06 are the most important, and then A10 is the most important. And these yellow bars show the failure probabilities. And the reason that A01 is the most important is because it has the highest second highest failure probability, and also many classrooms, which is represented by these gold-colored bars. So this makes A01 most important. Then A06, which has a smaller number of classrooms, but have relatively high failure probability. So we get this importance. Then now for this one, this is the second most important building, and this is because it has a very high failure probability, though it has not much classrooms. On the other hand, AO2, which repeatedly appeared in many failure rules because it has a large number of classrooms, but because it has too low failure probability, its importance is measured relatively low. And in this way, you can calculate the relative importance of the buildings. So in conclusion, the school reliability can be efficiently quantified using MBN and BRC, and we just saw how various probability quantities can be computed. And as a further exercise, if you want to give it a go, I suggest first you can repeat the process for school B, and also you can use it you can do another analysis combined with transport. So for instance, this is just a map, and this is school A that we considered. And there are two bridges. And if you're interested in the access to the education from this node, then this requires two things guaranteed. First, the transportation needs to be connected, and second, this school needs to be in operation. And if we need to consider these interactions, then we need to redefine the system function to include these bridges, and thereby we can decide the accessibility to education from this neighborhood. So, and this can be found on our you can find the example solution here in this third set of Jupyter Notebook. So you can take a look over here as a solution. That was me, and if give it a go by yourself on Google Colab, and if you have any questions, just put it on either Q&A or chat, or you can raise your hand, then I will unmute your mic. Thanks.
Thank you, June. Do we have any questions?
No. I hope it wasn't too complicated.
I don't know if people have have a look beforehand on the GitHub repository, or just to get familiarized with the material before the session.
Yeah, we could give it a time.
Yeah.
And so you could just try now, and if you have any questions, or any other miscellaneous things, we will also be happy to chat about.
So, can I ask one thing, June? So the last bit on the importance of buildings. So you have plotted the importance now for the buildings in one school, yeah?
Yeah,
So,
buildings for, yes.
yeah. So this is now you have defined importance in terms of the number of classrooms a building has and the failure probability the building has.
No, it is defined as I calculate the CPIM, the conditional
Uh-huh.
probability importance measure.
Uh-huh.
This is defined as the component failure probability
Mm.
being conditioned on the system's failure event being conditioned on the system's failure event. So in
Okay.
this way, it measures the relevance between the component failure event, each component failure event to the system's failure event
Okay.
to measure the relative contributions.
So it's basically the component failed given that the system failed.
Yeah, so it is
Okay.
an updated failure probability
Okay.
if we assume the system's failure.
Okay.
Then
So it
usually,
just sorry, so it just say for so you're not what do you say? You're not defining the condition for importance. So
no,
the measure the CPIM
uh,
that itself is computing the importance. So
yeah.
I think the number of classrooms a building has
Mhm.
inherently guides that decision, isn't it?
Yeah, so it is implicitly considered,
Yeah, in
but
the
mhm.
in the decision. Yeah, I understand.
Yeah, so I just wanted it. So it is always better to sense check the
Mm,
importance measures, which are a conversion of many things.
yeah.
But usually, especially when it comes to this complex networks and connectivity and maximum flow,
Mm,
this becomes less intuitive. So even if we are
mm,
just trying to understand its topological importance and failure probability,
mm,
usually we get quite counterintuitive measure
mm, mm,
outcomes. So it
mm.
is not always easy to understand
Exactly.
what's
So
going on.
this
Yeah,
kind of measure is really helpful to to then infer the results.
yeah.
Yeah.
But there is another importance measure, which is bomb measure. So
Mm-hmm.
then it is the other way around, that it measures the uh, the system's survival event
Mm-hmm.
conditioned on the component survival.
Okay.
Then many of the times these two importance measures, although they are measuring the very similar thing, they give completely different results.
Okay.
So usually it is better to look at different importance measures and make
Yeah.
some informed
Okay.
decisions. Yeah, they
Okay. So
are.
it's not so so the building that this method now found as the most important may not be the
Uh,
same if you did the other way around.
yeah,
Okay.
it's
Okay. That's interesting. Yeah.
yeah. Then we are tempted to do this or this,
Yeah. Probably do both
optimization.
and see. Yeah, exactly.
Yeah, and so the rationale behind this uncertainty-based optimization is that usually these important measures are limited in terms of their relevance to the actual decisions that we are interested in. So we
Mm-hmm.
are directly trying to find out the solutions that just directly,
Yeah.
yeah, because these important measures are for the cases where we cannot afford the optimization cost for
Mm.
whatever reason. So we are
Mm.
just it's kind of approximation and
Yeah. Yeah. So this is very helpful.
thanks.
There's a question. Can you read it, Gian, or you want me to read it?
Yeah, I can read it.
Okay.
So information about I should perform precision analysis means observation. Try to verify. So I this is a really good question. Thanks. So the next step should be always definition of system failure. It is not always evident. So in this case, because it is a complex of buildings, so I wouldn't define a network, but rather here I think the availability of classrooms was the most important, the critical aspect to continue the education. So I define the system function as if the available number of classrooms is enough. Then if it is components, if it is a network, transportation network, then yes, then you need to build a network of these roadways, and you need to decide which OD pairs you look most critical. The most conventional practice is to set the origin as one of the entries to the highways or airports and main rail stations where most of the emergency goods are distributed. And the destination nodes are these neighborhoods, which can be many or just one, depending on the purpose of the analysis. So the third step I would say is to define the system's objective, which will lead to the system function, and that will be all. Then you are all set, and we'll be able
Can I
to.
just interrupt? So just to
Mhm,
make it a bit more clear for the question,
mhm,
so say for example, we just go with his lead. The first,
mhm,
I need to collect information about the buildings. Done.
mhm,
For this particular problem, where we have say 5 buildings in a school compound,
mhm.
this is the problem for now. We are not dealing with the road network yet. So what would be the next step three? Would be you define the system objective, which is identifying the number of classrooms available and decide if that leads to the failure or survival. S- Is that step
Yeah.
three?
Step three,
Mm,
define the system's objective.
yeah.
So if we define that the system's objective is to guarantee that at least 70% of the classroom should be available to continue
Hmm.
the education, then that will be the objective.
Objective,
Yeah,
yes.
then based on that objective, we can mathematically formulate the system function.
Hmm. So that's step
And
four.
right,
Yeah.
yes,
So
step four.
step four is formulate the system
Yeah,
function.
numerically translate the
Yeah. Objective.
illustrative system objective.
Yeah.
Then step five, run the analysis in the very similar procedure that we just saw now.
Yeah.
Mhm.
Okay. There's another question.
Uh, Thank you, Johnny. That is a very good question. So I would say, so for transportation networks, this is what I've been investigating for quite a long time. And there are there are larger two ways in my opinion. So the first one is we just define each origin destination node. So for instance, if there are a couple of critical regions for emergency activities like airports or highway entries, then we set those as as the origins. Then we look at each neighborhood, which constitutes one destination. Then then that means we are creating as many system events as the number of neighborhoods that we are targeting. Then we can run the separate analysis over each of these systems. And this way, we can compare the vulnerability in terms of the connectivity to these critical nodes from each neighborhood, and we can compare the risk. And on the other hand, we can do the full network community setting where we have a bunch of destination nodes which represent the neighborhoods, and we have a bunch of critical nodes. Then we can define the system failure as if half of the neighborhoods don't get the necessary connectivity, then the system as a whole can fail. In this way, we can provide more collective view in terms of how these horses then work together. Does that make sense? If this is
Yeah.
confusing, just drop me another message. Yes.
I think
Yeah,
we
thanks.
can open his.
I think it was
I
answered. Yeah. So um,
okay. Yeah.
yeah, so it is usually that a giant transportation network that serves a community has many origin destination pairs that it is trying to connect, which means that this giant transportation network is a set of system events. So usually what we end up is we define numerous system events and we calculate each of these events. And I think this is very closely linked to the disaster equity that is now becoming a heated topic, that if the neighborhoods are getting equally distributed risks, or if somebody is bearing more risk than the others.
There's another question.
Right. Thank you for the question, Abbas. So I use this extensive damage parameters because that is when the building cannot be used immediately without any repair. So yeah, so I use that one as the parameter. So that's why we had only one set of parameters for the fragility.
I think that explains that. Yeah.
Mhm.
So it's the third damage state that we used in the fragility function.
Yeah, I think that's most conventional
Yeah.
when we are trying to analyze whether the building can be used.
June, I see some. Sorry, I think I deleted some.
Mm.
I see some more tutorial available in your link. Do
Mhm.
you want to explain like what problems they are dealing with in case people are interested to check?
You mean the 3 Jupyter notebooks?
Yeah.
Right. So the first one is the one that we saw in the last presentation with very small network with these 5 edges.
Yeah.
So, and the third one is where you can combine with these transport bridges.
Mm-hmm. Okay.
So yeah, it's quite addictive when you just start producing all these new system functions. So I just give you kind of a glimpse of how these system functions could be
Yeah.
changed. And so
No,
yeah, and
what I'm saying is if you wish to just open and explain a bit on that transportation integrated one, I think people
uh-huh.
are interested because they were asking questions about the transportation component. So
All right,
it might be of interest since we have time.
right. So then I will share my screen again.
Yeah, please.
So again, here in this tutorial, if you run Google Colab, then we can use this GitHub again. So if we take this one, I changed the really nothing, but I just added this bridge information. Isn't this? All right, so I just added the bridge information. So here I just brought this number, 7% and 13% of failure of these two bridges that I showed you in this map. And this is based on the previous project by Asana and other colleagues in UNESCO chair and Kagayan Deru. So I just added these two bridges in these variables and CPMs. And what is changed is in this one. So now we not only check the variable classrooms in this system function, but we also look at whether these two bridges have survived. So for this one, I set up this small graph here, where it consists of these 6 nodes and the 6 edges that connect these nodes, and the bridges are affect this node connecting M5 and 6, and this node that N2 and N3. Then within this system function, it checks two things. First, it checks if there are enough number of available rooms, and second, it checks in this G if the bridge is not available. Then we remove the edge from this event, this graph. Then we check if it has passed from this node N1 to M4, which is the location of the score, and if the both are guaranteed, then we return system state as survival, and if either of the if any of these conditions are not met, then we are returning the failure. So the reason that I created, so if you look at this is actually a very simple parallel system that you can decide this connectivity by looking at any of these bridges has survived. But the reason that I created this network is because I wanted to show how we can use how we can define a system function by using this network analysis. So in case we have more complex topology and or other edges can fail. So it is most typical to consider the failures of the bridges because they are usually the most vulnerable components in a transportation network. But there are cases where we consider the paved roads failures as well, which are the case when we have either ruptures or ground failures, or in this kind of a densely connected urban areas, the collapses of adjacent buildings are also one of the failure mechanisms of these paved roads. But in
Because
this,
their brakes will block the road.
yeah, and so yeah, but in this case, we're just considering the two braces. So the only part that was changed is the system function, and everywhere else is the same.
Okay. So when you have these two sets of but we don't have a graph for the school component, right? In the analysis, we don't need to have a graph for the school.
No, because because we
We're
are
not
not interested in network connectivity or measurement flow, or any other network behavior.
Okay.
So networks are a very specific data type that have these nodes and edges, and that these component interactions take place only through the connected edges. So whenever we are interested in this very limited the constrained ways of interactions, then we can use network. But otherwise, network is can be redundant.
Mhm.
Mm. If there aren't any more questions, then do you think it is a good idea that we close the presentation early, or what do you think?
Um, if anybody is still trying and if they wish for us to stay a bit longer, please put a message in the chat or Q&A so that we don't close early. But if you would like to take it in your own time and try and then come back to us via email, you're more than welcome. So if there are no comments from anybody, we
Okay.
can
How about this
close.
one then?
Yeah,
We just stay here for a few more minutes,
yeah,
and if and we take people leaving as a message that they are done with the exercise.
yeah. Okay,
And as long as they are in this session, then we can
okay.
wait, just in case they need
Yeah.
further.
So in that case, I think I can present the closing section so that we have some information to share with you. And if people would like to leave after that, it's fine. So let me just share my screen again. So but again, thank you all for joining us for these 2-day sessions. We hope you have enjoyed, and we it's a lot of material that is being shared over the 2 days. As I mentioned in my session and June session, we are very happy if you get in touch with us for any additional information or help with any of the material that is being shared. So with this webinar, we at the UNESCO chair, we are closing this webinar series for this academic year. So it's been a very rewarding journey for all of us. We have about 30 plus sessions run over the last 3 years or so, and we have connected with over, I think, about 3,500 people or from 100 plus countries, which is a very, very impactful information. So thank you all for joining us for all our sessions, including today's, and we hope we will actually, am I sharing the screen? Yeah. We hope to actually continue the work on this kind of webinars and courses in the coming year as well. So we see that some of the sessions have been very well received, and we are, we could rerun the sessions in the future if there is interest. And after this session today, we will be sharing a link for collecting your feedback and any suggestions for us as we go forward. So please let us know what is the need, what kind of sessions, what kind of courses or modes of presentations or delivery that you would really like us to do. So we have um, we have connected to all of these countries that are shaded here with a lot of participants from Philippines all the way to Slovenia. And for the next year, we are thinking to align our presentations and webinar series on these 6 research lines or themes. And I'm sure all of our previous presentations and webinars also belong to any one of these categories or multiple categories. And it would give us a much better understanding of our future plans. And also we will be producing a schedule of all the webinars that are in the plan. So you can plan ahead and book with us or register for the events and so on. So one other thing is you are also welcome to propose topics and also welcome to present with us. So if you have a research, a very interesting research that you would wish to share with the community that we normally reach to, please do get in touch with us, and we will arrange to have presentations and webinars with you. So I think with that we can close I'm going to share the link in the chat now. I think I should stop sharing. It would be great if you could all take a minute. It's less than a minute. Sorry, I think I didn't share it with everyone. The link is in the chat now for the feedback. It's
I
the
think it is not the feedback forms link.
no. Oh, sorry. I think I
Yeah.
did the GitHub link. Sorry. Let me go back. Here is the link. I hope everybody can see the link now. We will also send the link via email for those who couldn't join today and they were present yesterday. So we can send this again. So please do take a second, maybe 10 seconds to just fill the form and let us know what you think.
Thank you, Dexter.
Thanks, Dexter. You're still up. It's
All
very
right.
late. It's late for you.
Thank you.
Thank you for staying with us from Philippines. So as Jiyun mentioned, we will stay on until the end of the session that is planned. So we have another 30 minutes. You're welcome to try the material on the GitHub and leave as you finish, as you feel you are confident in accessing and doing the material, or we will be available to answer your questions until 4 p.m.
Right.
Thank you.
Thanks.